This is my Lab 5 report, Faraday's Law. In this lab, I first do the experiment, drop a powerful magnet from the top of the aluminum foil and measure the time passed for it to leave the bottom. The result of the average delta t is equal to 0.279 seconds. And then I do the computational model, examine the interaction between the bar magnet and the aluminum foil. Use a computer simulation to test the experimental result and plot the velocity versus time graph. The result is 0.243 seconds. These are the physical principles I use. First is a Bell-Savart law. I use it to calculate the B field of the magnet and then in turn calculate the magnetic force. The Faraday's law is used here to find the relationship between the change of flux and current. Newton's second law is used to predict the motion of magnets, and Newton's third law helps us find the relationship between the magnetic force on magnet and the magnetic force on loop. Use Ohm's law here, we will find that I is equal to the potential difference divided by the resistance. And if you look at the picture on right below, you will find the final relationship is that the current is equal to the change of flux divided by the resistance. This is my experiment. See the table on the left. I repeat the experiment for 5 times and calculate the average delta t is equal to 0.279 seconds. So why use a cardboard tube rather than ferrous tube? Our aim here is to calculate the magnetic field induced by the aluminum foil. But the ferrous tube is also conductive, so it will increase the total magnetic field and make the result inaccurate. And the second question is the difference between the falling through the conductive tube and the free space. I will actually specify it in the following slide. But basically, the magnet falls faster in free space because it is solely affected by gravitational force. This is my computational model. In the first step, I just insert all the geometry fact of the tube that I use. In the second step, I calculate the magnitude of the magnetic dipole moment, which I have already calculated in Lab 3. In the 3 and 4 step, I just define the magnetic field and the change of flux. The 5th step is basically use the Bell-Savart law to calculate the magnetic force on loop. And by using the Newton's third law, we will get the result of the magnetic force on the magnet. For the 6th step, we add all the force that we have exerted on the magnet and calculate the net force and use the Newton's second law to predict its motion. This is the computational model result. This is my result for it. If you see the graph on the right, you will find the velocity increases in negative direction as time passed by. We have already known that in free space that the velocity versus time relationship is a linear relationship, and the v increase with constant acceleration in negative direction. But through the aluminum tube, it's non-linear, and acceleration is changing. The velocity is actually increased much more slower than in free space, which is actually makes sense because it's not only affected by the gravitational force, which is pointing downward, but also affected by the magnetic force pointing upward. For the question, first, which color corresponds to clockwise current and which color corresponds to counterclockwise current? In this case, that I assume the north pole is pointing downward. So you will find the blue is represent the magnetic field of the bar magnet. Because the velocity is also pointing downward, we will find the change of the magnetic field is pointing downward. According to the right-hand rule, the current is clockwise, and its counterpart, the red one, is represent the aluminum foil, and the current is counterclockwise. If I flip the magnetic dipole will be in opposite direction, but the the velocity of it will always pointing downward. So the bar magnet will have opposite current direction, which is counterclockwise, and aluminum foil will have clockwise current. So the next question is how to compare the experiment and the simulation. The result of my experiment and the simulation is largely the same, but the simulation is absolutely much more accurate. Because for the experiment, there will be some other conductor materials in the surroundings affect the result. Here's my conclusion and answer for what if question. What if the resistivity of the conductor were reduced as close as possible to zero? If the resistivity reduces to zero, the resistance will be also close to zero. So the current will be infinitely large, and so the magnetic force. In this case, the magnetic force will be much more larger than the gravitational force, so the magnet will be moving upward and it will never fall. Second question, what if a hose or slot were cut into the tube? I think there is no current at hose or slot at this point, so the total current will reduce. That is all. Thanks for listening.